Sounds good. Okay, so you got some handouts, or lots of handouts. Oh, what the? That's not it. You've got kind of most urgent, or not urgent, but kind of most important for now is the practice test. Okay, so what you're going to do for the practice test is, well, you can read through the front. The front is just an outline of what you can expect, or what I expect you to know for this test. Okay. And then on the inside, there's a couple of multiple choice practice questions and some long answer practice questions. Okay. Some of these multiple choice are going to be theoretical, right? So do you know what it means for two things to be disjoint, for example? Right? They have no outcomes in common, that kind of thing. So some of this stuff is just theory and it's covered in the multiple choice. But then there's also some applied stuff in the multiple choice that we do. So I've just given you some practice for that. Okay. And then the long answer practice is exactly as it sounds, practice for the long answer questions. Okay. What I want you to do, we're going to go through this in class on Wednesday together. Okay. But what I want you to do is, before then, if you attempt these, you don't have to know what you're doing exactly. You don't have to have it right. As long as you show me that you have put in some time and done these questions, done your best, kind of worked through it, worked at it, okay? Multiple choice and the long answer questions. Then at the beginning of class on Wednesday, has to be at the beginning, otherwise we'll go through it together. Right. But at the beginning of class, I'll just walk around, you quickly flip through, show me that you did some stuff, you worked at it, you tried, and I'll give you an assignment mark, 100% assignment mark. Pretty good. Fair, I'll take it. That's pretty good. Right, so make sure you do those. Those are easy assignment marks, way easier than something like assignment 3, for example. What's happened in the past is people have spent a lot of time on the assignments, but forgotten to do the practice test. But the practice test is a guaranteed 100%er. Just do the practice test instead. Right? Assignment 3 is due on Monday, so you have a week to work on it. Okay? What you'll notice is that it's basically practice for 2 of the long answer questions, normal distribution and the binomial distribution, which we'll cover today. So if you don't have, onto my third handout, if you don't have these from last day, come grab one here, because we'll go through them today. Any questions before we get started? Okay. I slept at the airport last night, so I'm not exactly on my A game. It's a rough night. Anyways, we almost landed in Kelowna. Tried, went back to Vancouver. Any hoodle. So you'll forgive me if I'm a little off. Okay. So just kind of scrolling back to what we were doing last day, I wish we had time to do more of a review, but how we'll review is just kind of quickly flipping through the example that we kind of ended on last day. Set the mood a little bit. Oh, too much. There. Just doesn't help when it's glaring on there. Okay. Remember this example where we had a cereal manufacturer, right? And so they're filling their cereal boxes and they want to make sure that it's filling a certain amount, right? Follows a normal distribution with a mean of 16.3. There, I have it there. And a standard deviation of 0.2 ounces. Weird, right? And then we were able to answer questions like, what proportion of the boxes will be underweight? Underweight being anything less than 16 ounces in this case. Remember when we're talking about proportions, we're talking about the area under the curve. In fact, any of these three P's, I'm asking for the area under the curve. Proportion, what's the probability, what percentage of boxes are underweight, right? Those are all looking for areas under the curve. And so we developed those concepts and then we applied them in this example last day. We didn't quite finish though. I think we got through C. And then, oh yeah, I got you guys to think about D. You all went home and thought about it, lost some sleep over it. No, because you knew what to do right away. So now we have this other situation, right? So if they want to publish a guarantee, like no more than 4% of boxes weigh less than this amount, right? What amount is that going to be? So now we'll kind of jump in. So I'm just going to continue on these notes. And here's what I'm going to do. February 4th. I'll just give it a little highlight here. More so I know where new stuff is from the old stuff. You presumably have these notes somewhere for you. So D, what we want to know is, okay, so we have some situation like this, remember, so it follows, so the weights of the boxes follow a normal distribution with a mean of 16.3 and a standard deviation of 0.2. So that hasn't changed, right, for this whole question. Now we want to know, okay, so we're going to force this area, right? Because what we want to guarantee, right? We want to be able to publish something that says, okay, well, we can guarantee no more than 4%. That's an area under the curve, right? A percentage is underneath the curve, right? An area under the curve. And so no more than 4% weigh less than this amount. Okay. So now we're working backwards. Right? We're forcing this area to be 4% and then finding what amount is that? Okay. So last day I sketched out this pendulum, as I call it, where before we were starting with some observation. We converted it to a z-score and then use that z-score to find the probability. We went from x to a z by z as x minus mu over sigma. And then once we have a z-score, we can use using the z-table. And we talked about how do we use the z-table. Was that last day or the day before? Last day. I think. Last week. Feels safe. Okay. So that's how we've been going so far, right? We've got some observations that we want to know the probability of, but now we've got this kind of reverse situation where we know the probability and we want to know what x is. And so we can use the same motion backwards. Okay. So what I'm going to do is I'm going to put a little question mark underneath here just to indicate that that's what I'm looking for. And I'm going to force this area to be 0.04, right? 4%. But what I like to do, or what we have to do when we're working with these percentages, is we have to convert them to decimals, right? So 4% is 0.04. Okay. So if you had to guess how to do this problem, right? Knowing this situation here, so now we're told that, okay, this probability is 0.04, right? We can use the Z table, work backwards, right, from an area of 0.04. And if you don't have a table with you today, I've got some extras here. You can come grab one, borrow it or grab one if you don't have one yet. First thing we know, right, is, I know I make you do the walk of shame to get papers if you don't have them. First thing we know is that it's going to be on the negative side, right? Just because we know that here in the middle we've got 50% to the left, we're only talking 4% to the left, right? So it has to be below the mean. So then we know for sure we have to work on the negative side. All these table entries are areas under the curve. So what we're going to do is we're going to try to figure out which of these values is closest to 0.04. Don't be fooled. There's a very nice looking 0.004, but that's not it, right? It's very easy to kind of get caught up in finding something nice like that, but you have to pay attention to your zeros. Okay. So 0.04. Get closer, closer. Oh, there. One of these. Looks like this one's the closest. You could just quickly use your calculator to figure out which one's closest. So you're rarely going to find one that's exactly bang on. Okay. You just want to find the one that's the closest. So, gotta scroll down. Keep an eye on that one. What is it? There. So now we know, okay, well, 0.04, that's pretty close to 0.041, 0.0401. So now we can backtrack to find the Z-score that corresponds to this value. And so from here, you can branch out, skip the beat. So I get a Z of negative 1.75. What I'm gonna do, as far as showing my work goes, I'm just gonna write it out in a sentence. And what you probably noticed is that I use the same sentence over and over and over again, right? And I encourage you to use the same one, right? It's not plagiarism in this case because I'm telling you to use it, right? It's just the safest option. So I'm going to write out exactly what I did using the Z table. We find the table entry closest to 0.04 is 0.0401. So far, exactly what we did, which corresponds to Z equal to negative 1.75. I hope. Is that the one? What a relief. Okay. So now you have a Z score, right? Just looking up here. So now you have a Z score. Now you know Z, you know mu, and you know sigma, so now you can solve for X. Right? And that's where you want it to end up. So now we have Z is, Z is still X minus mu over sigma, but Z is now negative 1.75 which is x, which was the one we're trying to solve for, minus mu, which is 16.3, over sigma, which is 0.2. So 1.75, whoops, negative times 0.2, we get negative 0.35 is x minus 16.3. And then add 16.3 to both sides. I get x is 15.95. So now what we're saying is that, trying to keep it all on the same page here, we can guarantee that no more than 4% of boxes weigh less than 15.95 ounces. So therefore, we can, I'll put quotes around it, guarantee, we can never guarantee anything, but we're confident. We can guarantee no more than 4% of boxes weigh more than 15.95 ounces. Cool. When we went to use our table, right, we were able to go to the 0.04 right away, right? Because the table gives us only the area to the left. Right? And so the next question shows you kind of the opposite. Part, let me just nab it here. How heavy are the top 25% of heaviest boxes? Kind of a switcheroo question, but it's the same type of question, right? We're given a percentage and now we have to work backwards. So blah, blah, blah. Oops. I better put in another page here. So part E. Oh, any questions about part D? I know we're kind of jumping into the thick of things here. Doing okay? Okay. So part E is going to look like this, right? So we've got still the normal distribution and it's still centered on 16.3 and sigma is still 0.02 or 0.2. But now, at some point here that we're going to try to find, or that we will find, are the top 25% or 0.25 of the heaviest boxes. Same situation. Right. This value is the cutoff for, well, the top 25%, but also the lowest 75%. So you're going to use that fact because the table only gives you the areas to the left. And so to use it to find your Z-score, you're going to want to find first the area to the left of that value, and then you can go to your Z table. Or if you wanted to get sneaky about it, you could remember that you've got symmetry. Right? So even if you went to the lower end and found 0.25, you would get a negative Z-score, but Z is symmetric around 0. So once you found that negative Z-score, you could drop the negative. You don't have to. It's just if you wanted to get sneaky about it, and it's totally fair game. I'm gonna do it the same way that we did the other one, right? Not trying to get sneaky here, but if you see that connection of the symmetry, right, and going to the lower end instead, then that's fine. Okay, so I'll write out my blurb before I've even done it. Using the Z table, we find the table entry closest to 0.75 is, well, now I got to do the work. But that much you can just write out without even doing anything. So now I'm on the positive side. Notice how I'm calling it a table entry. I'm not pulling that out of nowhere. It actually says on here, right? So when it says table entry, it means one of these values, right? The areas under the curve. So we want 0.75, or what's closest to 0.75. I think here we go from 0.7486 to 0.7517. I need to use my calculator. 0.75 minus 0.7486 is out. Is 14 away. Well, 14. 14 in my mind. 0.0014. Whereas this one is 17 away, quote unquote. So then this one's closest. You can just do some quick math. Even if you pick the wrong one, I would take away half a mark. But as long as you follow through with that value, you're okay. I'll consider it a typo. So 0.7486 is the closest value. I'll jot that down before I forget. Which corresponds to Z equal to, where are we here? I'll just do it on mine. I've got 0.6 and 7, 0.67. Is that what you guys are getting? Z equal to 0.67. Just to show you what I mean by that symmetry and going to the negative tail, what you can do is you can find the value closest to 0.0 or 0.25 on the negative end. And what you'll find is that it is negative 0.67. And then just drop the negative because you're on the other side. So that's what I mean. Fool around with that if you want. So now we have our Z score. And so now we know Z is X minus mu over sigma. Z in this case is 0.67, which is X, which was the value we're trying to find, minus mu, which is 16.3 over sigma, which is 0.2. So 0.67 times 0.2, solving for X, right? 0.134 is X minus 16.3. Add 16.3 to both sides. I get 16.434 X. Plus, notice how I'm not rounding. Unless the decimals are out of hand, like here, we're only getting to 3 decimal places. So I'm just going to keep them in case it matters, right? Because we're talking 16.3 ounces with a standard deviation of 0.2. So maybe these little decimal places are going to matter. right? So I'd rather keep them and display them and then let whoever's reading my report do whatever they want with them. Right? So unless the decimals are out of hand, just keep all of them. Okay? And you'll know when they're out of hand. Another value or another formula that you could use, if you look at your formula sheet in 3.1, right? I've solved for x. Here, I like just having one formula and just solving for whatever I need from it, right? And so me personally, I don't like to have this formula. So on our formula sheet, right, we have z is x minus mu over sigma. In general, if we try to solve for x here, right, we would get z times sigma is x minus mu, and then x would be, how do I have it there? Mu plus z times sigma. Right. And so this is on your formula sheet. So if you wanted to use that as well, or instead of just solving for x every time, that's fine by me. I just prefer to solve for x every time, but it doesn't matter. Notice that that's what we've been doing, right? Z times sigma plus mu. Any questions about that one? I guess you should write a little blurb. I'll do it over here on the side. Therefore, the top 25% of the heaviest boxes, heaviest boxes weigh more than 16.434 ounces. I guess I'll put this kind of off to the side. Has nothing really to do with anything. Just kind of sprung up in my mind to show you. Any questions about that? Okay. So what we're going to do, we're going to get into, oh, and I have the R commands for solving these, right, on the sides there. That's just if you're curious, if you want to see what R does, but we won't go into them here. Section 3.2 is just really brief about QQ plots. And so all of our analyses that we're going to do in this course assume that we have a normal distribution. And so when we're assuming that we have a normal distribution, sometimes we need, I don't know, some other way to show that we have a normal distribution instead of just doing a histogram and saying it's normal, right? And so the QQ plot helps us do that. So a perfectly good option, don't get me wrong, is just to plot your data using a histogram. Does it look approximately normal? Yes, great, you have a normal distribution. Okay. The QQ plot is going to look something like this. It's going to plot your actual data points, right, against the theoretical data points. Right? The theoretical data points are going to be that smooth line with that same mean standard deviation that you have in your data, right? Where would it be if it was perfectly normal? And so that's what this line is here. And then the QQ plot plots the theoretical quantiles, doesn't matter, the theoretical points against the actual or the sample quantiles. If they're the same, well, in this case, this makes sense, right, if they're the same as you go along here, they would be on this straight line. So in the lab later on, what you'll see is you'll make a QQ plot. And I've got the code for doing it down here, or it's in the lab manual. But what you're going to be looking for is, are these points essentially on this straight line? Right? If you have a perfectly normal distribution, all these points will be exactly on this line. Of course, because we're talking about samples, right? We're not going to be exactly on the line. We're only going to be concerned if we have this huge kind of S curve around the line or just huge deviations, then we probably don't have a normal distribution. Here, I use the IRIS data set. It's kind of a famous teaching data set. It's really boring. It's on the sepal width and length and the petal width and length for 50 flowers from each of 3 species of iris. The species are Iris setosa, versicolor, and virginica. In case you care, doesn't matter. There it is. Okay. So it's kind of a go-to data set for showing stuff like this. Doesn't matter. So a QQ plot, really, at the end of the day, it just helps us evaluate if we have a normal distribution. If you're finding it hard looking at a histogram and saying, oh, that looks approximately normal, right? You can back it up by a QQ plot. At the end of the day, they're going to look about the same. Right? Any questions about that one? There you have it, QQ plots. Check. So 3.3 is on the geometric distribution, which we're not going to cover. So, but I couldn't change the numbering, so I had to have it on there. Not covering. Moving on, 3.4. We are going to do 3.4 on the binomial. Even though the binomial, you'll see it takes up quite a bit of space on your formula sheet, but it's not that big of a concept if you extend it from the tree diagrams that we were doing earlier, right, in chapter 2. So they're just going to be a way to handle a situation where a tree diagram would get out of control. Right? And so a binomial situation is when there are only 2 outcomes, okay, or a situation where you can boil it down to 2 outcomes. Right? Think about, right, you get letter grades in a class, right? So you could have A, B, C, whatever. I know there's more levels, but, right, or you could boil it down to pass, fail. You could even boil it down to A, not an A. So all these situations where you're able to just put it into 2 categories, you have a binomial situation. Yeah? Kind of a yes, no, success, failure. Right? And a lot of the time we're going to call something a success, right? That's going to be the outcome that we're interested in. If you're looking at kind of diseases, whether someone died or they survived, right? Surgeries, that kind of thing. Again, pass, failed, right? So whenever you're able to sort things into just 2 categories, 2 distinct categories, you have a binomial situation. So, a lot of new terminology in this section. That's why I don't like it very much. This doesn't serve us that well later on. But what we're going to end up talking about is the number of trials, right? So how many trials do we have at pass fail, for example, right? Or success failure. And then what this is going to help us do is we want to know, well, what's the probability of K successes? So K is just kind of a placeholder for however many successes you want to know the probability of seeing. Okay? I know I stole this example because I don't shoot hoops. I'm shooting hoops. And I know the probability of each shot going in is 0%. No, 0.2. If I shoot 3 times, what's the probability of exactly 1 success? We know how to solve this problem. We have one way of solving this problem. And so there's 2 ways, of course. Using a tree diagram, which is how you already know how to solve this problem, or we can use a binomial distribution, okay? Because we have this, it either goes in or it doesn't. The tree diagram, I just kind of did a generic one here. You can see how it quickly gets out of hand. Right here, we're looking at just 2 outcomes each trial, right? And so 2 outcomes, that's a binomial situation. And so first trial, and then second trial, third trial, fourth trial, right? Each of these little sticks has its own set of wings. Actually, these 2 are sharing, which they wouldn't. I had to program it so it's not going to be perfect. Okay. But so you can see if you tried to make this tree, it just gets out of control, right? And so that's when we want to start using the binomial distribution to help us solve these problems. So if I say I guess I've let H be getting it in, I don't know. Making the shot. I think I was thinking of hit. Like, I hit it. Clearly, I don't shoot hoops. I don't know. And see my little mix up here? I got sloppy. I did the H prime, but H prime is just the complement of H. So what we would do, right, in a tree diagram, so okay, so first shot, I can either hit it or quit it. Hit it or quit it. So I'm shooting this thing 3 times. Yowzas. So that's what that tree diagram up above should look like, but they kind of merged the middle too because it got too wide. Mine got a little tight towards the end there. A little lazy, right? But so the question here, if I shoot it 3 times, right? First shot, second shot, third shot, right? Again, we have these consecutive events, right? Day 1, day 2 that you were dealing with, right? Midterm, final, right? These consecutive events. So what's the probability of exactly 1 success? So we want to look at these trees and say, okay, if I can only have 1 success, then that's going to be, if I start here, then after that, I can only have non-hits. Right. Nothing but the hits. There. That's one. If I didn't get one here, I've got two options, right? I could not hit one here, and then on the second shot I hit it, but then I can't hit it again. Right? That's exactly one hit as well. So that one. And if I don't hit it and I don't hit it, but then I have to hit it at the end. So we've got three options for exactly one going in. Each one has the same probability because you've got two non-hits and a hit. That was the criteria. Doesn't matter how you multiply them, right? So to get the probabilities at the end of each branch, right, you would multiply down the branch. 0.8 times 0.2 times 0.2. 0.2 times 0.8 times 0.2. Same value. 0.2 times 0.2 times 0.8. No, other way around. I made myself a super shooter. Anyways, you get the idea. So the probability of exactly one hit is this one, or this one, or this one. Right, so we can just add them up, which ends up being 3 times 0.128. Right? 3 because we have 3 ways of getting there. Each with a probability of 0.128. So we solved it. Probability is 0.384. What if I said I shot it 10 times? Now you need 10 layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yikes. Okay. So the binomial is going to be what helps us handle something like that, right? Where we just can't do a tree diagram anymore. Here, in order to be able to deal with any number of trials, we use the binomial distribution to calculate the probability of k successes in n trials. Okay, that's going to be important. K stands for the number of successes that we're interested in, and n is the overall number of trials. Right? How many times did you try to get k successes? And so if we just let x be a random binomial process, in fact, you can kind of ignore this part. It's just for show. How we're going to calculate this probability is with an actual calculation. So we've got this choose function. Have you guys seen the choose function before? And choose k. We'll talk about it. But this is called the choose function. So it's not a fraction. And like I said, we'll talk about it. But really what it's helping us calculate is how many ways can I choose, say, k successes in n trials, right? How many ways can I choose one success, exactly one success, in 3 trials? 3 ways. P is going to be the probability of a success. K, again, is the number of successes. 1 minus P is the probability of a failure, right? The complement. To the power of n minus k is going to be the number of failures. So I've got those outlined here. Notice that you only have this on your formula sheet. So you'll want to make sure that you know n's and k's and p's and q's. I say that, but they're also in there. Okay. 1 minus p is quickly going to be replaced by q. I think we've seen q before, right? I kind of snuck it in there. Tried to stick to p and 1 minus p, but q is going to be the probability of a failure, 1 minus p. And I think I even have it. Oh, it is on your formula sheet, where q is 1 minus p. So let's talk about this choose function. So every calculator, every scientific calculator that I've come across has the choose function. And so it looks like this usually, or something like it. So it has a value to the left, usually n, and then a capital C in the middle, and then a lowercase r, or sometimes it's k. If you have one of these calculators, it's the yellow function over the plus sign. And so how we're going to work it is usually, and I say usually in the notes here because obviously if you're not working with this calculator, it's going to be a little bit different, potentially. But I tried a few different calculators and they all work the same way. So if we want to do 3 choose 1, right, in 3 trials, how many ways can I choose 1 success? That's what we did before, and we found there's 3 ways. So what we can do is we can do 3 on the screen, and then second plus sign for the choose function on this calculator, because it's not that good besides for business math. Doesn't show you anything, you just trust it. And then you hit 1 equals 3. It's not very helpful because we had a 3 in there. So why don't we try a different one? So what I want you to do is just use your calculator just to confirm that you're getting these same values. So do 10 choose 2 equals, should be 45. In 5 trials, how many ways can we choose 5 successes? If you think about it, that would be following the outline. There's only one way for that to happen, right? So it makes sense that 5 choose 5 is 1. I want you to try to do the 100 choose 45 because, especially on this calculator, if you've got this one, it's really sneaky about showing the scientific notation. Okay. And so if you do 100 choose 45, so now you've got 100 layers of your tree diagram, and you want to know how many ways can I choose 45 successes? It's huge. So if you do 100 choose 45 equals, and on mine, it just has a little space between the 28, okay? And that's how you know that it's showing scientific notation. Okay, so I've got a little note here that whatever calculator you're using, just make sure that you're able to recognize when it's giving you scientific notation, right? Because this is huge, 6 point whatever times 10 to the power of 28. That's massive, right? That's how many ways you can choose this. 45 successes in 100 trials. And we can round it up with 10 choose 7. 120. Back to normal. Oh, look, a typo. I'll even do it in red for you guys. Where's the typo? You say? 3 choose 1. We wanted to know what's the probability of exactly 1 success. So K is 1. So the formula then is n choose K. So now we're kind of more familiar with this choose function. And P is the probability of success. We decided that the probability of me shooting it in is 0.2, so that's the probability of a success. K, in this case, we want to know what's the probability of exactly 1 success. So K is 1. 1 minus P is a 0.8. And then N minus K is the number of failures. If I have exactly 1 success, then I'm going to have exactly 2 failures. notice how this takes the same form as when we did it by hand, right? There's 1.2 in there and 2.8, 2.8 squared. And then you multiply it by the number of ways that you can get there. And we get the same answer. Any questions about that? How about this? For a little bit of a zip. We can find the mean and the standard deviation of a binomial distribution. In fact, we can use the normal distribution to find probabilities associated with the binomial distribution if we have a large enough number of trials. On your formula sheet, I think I have, mean and the standard deviation of B and then in brackets NP, right? Binomial, N trials, NP probability of success. The mean of a binomial is going to be N times P. How many trials did you have and what's the probability of success? If you think about it, if I tell you that I shoot it 10 times for nice numbers, and the probability of me getting it in is 0.2, how many would you expect me to get in? 2? Yeah? So that's exactly what we're doing, right? 10 times 0.2. So the mean is the expected value of our binomial distribution. In fact, later on in stats, if you keep going, which I know y'all will, the mean is often called the expected value, right? Because it's what we're expecting to see. It's the average, right? And so, same idea, less obvious though. The standard deviation we can find by taking N times P times Q. That's N, the number of trials, times P, the probability of each success, times Q, the probability of each failure, and then square rooting them. Luckily, you don't have to remember that. That's just on your formula sheet. Again, for Q, it's just 1 minus. So what's nice about knowing the mean and the standard deviation, now we can use z-scores to find probabilities, right, of some x. So here, I've got it on there, but now we can use z is x minus mu over sigma to find probabilities for binomial distributions. See a typo right away. So let's do an example just to show what we're doing here and what we're dealing with. So the S&P 500 index has a probability of 0.56 of increasing in any week. So this index, we've boiled it down to it can either go up or it can go down. We assume it doesn't stay the same. And so now we've got these 2 outcomes and that's it. So we have a binomial situation. So assume the change in the index, the indies, in any given week is not influenced identify whether it rose or fell in the previous week. That's a little bit, I don't know if that's a reasonable assumption, but I'm telling you to assume that, because otherwise we wouldn't have a binomial distribution. Let X be the number of weeks among the next 5 weeks in which the index rises. So we're looking at 5 weeks. So we have 5 trials. And we want to know first, how many possible outcomes are there each week? Each week, we only have 2 outcomes. Right. It can go up or it can go down. Oops, down. So each week, I'll add a page. Example 8. A. Is it 8? Yeah. Each week, we have 2 possible outcomes. Up or down, right? Which is what makes it a binomial. We've got them there, so I'll just steal them here so I don't have to scroll so much. Part B, identify what a success is in this case. So depending on the question, right, what we call a success might change. And I think I have that on your assignment 3, where it kind of changes midway. Yeah, question 3. So question 3 on the assignment is a binomial question, as well as the last long answer question on the practice test. It's also a binomial. And it'll be the last long answer on the actual test. I'm going to keep the order, well, besides the multiple choice, but for those long answers, I'll keep those in the same order. Right? Don't want to blindside you. So just memorize the order. A success in this case, we're told let X be the number of weeks among the next 5 weeks in which the index rises, right? Is the index rising, going up? What's kind of morbid, if you're looking at success rates of a surgery, for example, then in terms of calculating probabilities, you're not too concerned with, what's the probability of surviving, especially if you're in the testing phases. You want to know what's the probability of someone dying from the surgery. So in that case, right, a death would be a success. And so it's often kind of like a little bit backwards, right? The thing that we're more concerned about is the success. In this case, we want to know how many of these weeks is it going up. That's a success. That's great. And positive too. Part C. What are N and P in this case? N is the number of trials. I'm putting that on just as a refresher, and we looked at 5 weeks. So we had 5 trials. I'll just put in brackets here 5 weeks. Right, because let X be the number of weeks among the next 5 weeks in which the index rises. And P is the probability of success. Oops. Which it starts off by saying the S&P 500 index has a probability 0.56 of increasing in any week. So you want to make sure that that probability is actually matching the success that you're talking about. So in this case, 0.56. D, what are the possible values of X? Possible values of X in the next 5 weeks. It could go up 5 of the weeks, 4 of the weeks, 3 of the weeks, 2 of the weeks, 1 of those weeks, or even 0 of those weeks, right? You don't want to forget about the 0 option because it's possible. Unlikely, possible. So 0, 1, 2, 3, 4, or 5. And if you want to get fancy, you can throw curly brackets around there, but you don't have to. Set notation. What's the probability of the index increasing in more than 3, not including 3 of the weeks? So what's the probability that X is greater than 3 is essentially what we're asking. Well, if it has to rise in more than 3 of the weeks, not including 3, that's either 4 weeks or 5 weeks. And we know how to deal with that, right? Because they're saying, okay, well, we can find the probability of 4 using that formula, or the probability of 5. So we just find those two individually and add them up. So we have the probability that X is greater than 3 is the same as the probability that X is 4 plus the probability that X is 5. I'm going to solve for these. Solving these individually, only because they take a lot of room. So if you can squeeze them in on the same line, then fine. Right? But I'll just do one, and then I'll do the other, and then I'll put them back together. But you don't want to forget to do one. Right? Do one, do the other. So the probability that X equals 4 is, in general, right, we've got this, or I'll even do X equal to K here, is N choose K. So the choose function is just 2 round brackets around both of those values. There's no divisor in there. Right, so careful that you're not drawing a line in there. It's just N choose K, and then P to the K times 1 minus P to the N minus K. So the probability that X is 4 is going to be, well, N is 5. We already decided that. And now K is 4. So 5 choose 4. P, we already said, was 0.56. to the power of k, which is 4, times 1 minus 0.56 to the power of 5 minus 4. Can simplify this a bit. We'll start with 5 choose 4 and just get 5. If you think about it, makes sense, right? If I have 5 trials, that means I have 5 layers in my tree diagram, right? And then I want exactly 4 successes, so only one of them can't be a success. So as you move down, there's only one branch for each layer that satisfies that. Anyways, it's 5. And then I'll keep the 0.56 to the power of 4 there, while I simplify 1 minus 0.56 is 0.44 to the power of 5 minus 4, which is just 1. So 0.56 to the power of 4. Do you guys know how to do powers other than 2 on your calculator? It's the Y to the X button. If you don't, then just come see me and I'll, just after class, and I'll show you. So 0.56 to the power of 4, I get 5 times 0.09834496. No, you don't have to show that. I'm just writing those down so that if you're doing your calculations later and you want to check that you get the right number, then you can check there. So 0.56 to the power of 4, just double checking. Good. Now times 0.44 times 5. So the probability that x is 4 is going to be 0.216358912. And I'm going to be really careful not to round these because sometimes the difference in these probabilities happens somewhere around here. So I don't want to round too quickly. So I'm going to keep all these decimal places until the end. Now, I'm going to find the probability that x is 5. Just kind of jumping straight to the formula here. 5 choose 5 times 0.56 to the power of 5 times 0.44 to the power of 0. Anything to the power of 0 is 1, right? So I want to do 5 choose 5, which I already suspect is 1. There's only one way that I can hit every single time. So 1 times 0.56 to the power of 5 times 1. So it's really going to be 0.56 to the power of 5, 0.055073178. So the probability that x is greater than 3, not including 3, is the probability that x is 4 plus the probability that x is 5, which we just said was 0.216358912 plus 0.055073178 plus, oh, I should have saved it, 0.216358912, which is 0.27143209. Ah, what the hey, I'll just leave it like that. Now we also know the probability of getting less than or equal to 3. 1 minus that. How about F? What is the mean and standard deviation of the distribution? So the mean, mu is n times p, which in this case N, we had 5 trials, times P, which is 0.56. So in 5 weeks, if the probability of it going up is 0.56, I'm expecting it to go up on average 2.8 weeks out of 5. And it's okay to have a decimal there. And the standard deviation, sigma, is the square root of NPQ Q is 1 minus P. So sigma is the square root of 5 times 0.56 times 0.44 and those are just on your formula sheet. Is the square root. Don't forget the square root, 1.232. So sigma then is 1.109954954. In this case, I'll rounding to 4 decimal places. Sigma is 1.10. Oh, so much for that. Okay. I know I've used up my time, but now that we know the mean and the standard deviation, we can just as well apply the normal approximation, okay? And so that's the last little bit of 3.4 that we haven't covered. There's just one thing that you have to check before you use the normal approximation, and that's that you have at least 10 successes expected and 10 expected failures. So what you check is that N times P is more than 10 and N times Q is more than 10. Okay? So what I want you to do just for practice is go through this little example at the bottom, right? You can do it, and then we'll just do it right at the beginning of class next day. It's good practice for the practice test too. All right, see you Wednesday. Come pick up your assignment, your new assignment, all that paper.